Gravity is one of the trickiest concepts to understand. In our everyday lives it appears relatively weak. Gravity is, by far, the weakest of the four fundamental interactions. However, gravity is the most significant interaction between objects at the macroscopic scale, and it determines the motion of planets, stars, galaxies, and even light. Gravity was one of the first forces to be recognized and is at the heart of the first laws of motion to be defined in physics. Yet despite this, gravity remains one of the least understood forces of all. What is gravity? Gravity, in mechanics, is the universal force of attraction acting between all bodies of matter. By Newton's law of universal gravitation. Gravity is the universal force of attraction acting between all bodies of matter. Gravity may cause apples to fall from trees, our feet to stick to the pavement, and the International Space Station to orbit our planet, but if we really analyze it, no such force actually exists. Gravity is accurately described by the general theory of relativity, proposed by Albert Einstein in 1915, which describes gravity in terms of the curvature of space-time, caused by the uneven distribution of mass. That's really complicated. Let's actually know what is gravity. In 4th century BCE, Aristotle made his statements on gravity. Aristotle believed that objects fell towards the Earth because the Earth was the center of the universe and attracted all the mass in the universe towards it. He also thought that the heavier objects fall faster. Aristotle's view was widely accepted throughout ancient Greece. In the mid-16th century, various European scientists experimentally disproved the Aristotelian notion that heavier objects fall at a faster rate. In the late 16th century, Galileo Galilei's careful measurements of balls rolling down inclines allowed him to firmly establish that gravitational acceleration is the same for all objects. Galileo postulated that air resistance is the reason that objects with a low density and high surface area fall more slowly in an atmosphere. In his 1638 work Two New Sciences, Galileo proved that the distance traveled by a falling object is proportional to the square of the time elapsed. One day Isaac Newton was sitting in a garden and saw an apple fall from a tree. While many people might not think twice about it, Newton asked a now famous question: why did the apple fall straight down, not sideways or upward? What force draws it toward the Earth? That simple question sparked a profound idea. What if the same force that pulls an apple to the ground also holds the moon in orbit around the Earth? Newton imagined the moon in orbit around Earth. If gravity didn't act on it, the moon would move in a straight line. But instead, it curves around Earth continuously, much like a projectile that falls while moving forward. He realized that the moon is constantly falling, but because of its sideways motion, it keeps missing the Earth, creating an orbit. In 1687, Newton published his work in a book that changed science forever, Philosophiae Naturalis Principia Mathematica, in which Newton's law of universal gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This means that larger objects exert a stronger gravitational pull, and objects that are closer together experience a stronger force. For example, consider two objects placed near each other. According to Newton's law of universal gravitation, object A exerts a gravitational force on object B, and object B exerts an equal and opposite force on object A. The magnitude of this force decreases as the distance between them increases. If we consider three objects, A, B, and C, each object exerts a gravitational force on the others. Object A pulls on B and C, object B pulls on A and C, and object C pulls on A and B. This mutual interaction illustrates how gravity acts between all masses, no matter how many bodies are involved. This is essentially how Newton described gravitational force. When an apple falls from a tree, it's being pulled toward the Earth by gravity. According to Newton's law, the Earth, with its massive size, attracts the apple, which has a much smaller mass. Even though the apple is tiny compared to the Earth, the gravitational pull is strong enough to make it fall. This law doesn't apply just to apples and Earth, it also explains why the moon orbits the Earth, why planets revolve around the sun, and why tides occur due to the moon's gravitational pull. In the 20th century, Einstein's theory of general relativity refined our understanding of gravity, describing it as the curvature of space-time. Still, Newton's laws remain accurate and incredibly useful in most everyday situations. Einstein's general theory of relativity completely transformed our understanding of gravity. Rather than viewing gravity as a force, as Newton had, Einstein conceived of it as the curvature of spacetime itself. This radical idea emerged from his famous thought experiments, imaginary scenarios that allowed him to visualize complex physical principles. One of Einstein's most pivotal thought experiments involved imagining a man falling from a roof. As he later recalled, the breakthrough came suddenly one day. I was sitting on a chair in my patent office in Bern. Suddenly a thought struck me: if a man falls freely, he would not feel his own weight. Both the falling man and any objects he dropped would accelerate at the same rate, making them appear weightless relative to each other. This insight became the foundation of Einstein's equivalence principle, which states that the effects of gravity are locally indistinguishable from acceleration. Einstein expanded this concept with his famous elevator thought experiments. He imagined an observer inside a closed windowless elevator. In scenario 1, the elevator is at rest on Earth's surface. The observer feels their feet firmly planted on the floor due to gravity pulling them downward at 9.8 meters per second square. In scenario 2, the elevator is in deep space, far from any gravitational influence, but is being accelerated upward at 9.8 meters per second square, matching Earth's gravity. Can the observer distinguish whether the force they feel is due to gravity or acceleration? No. In scenario 1, the observer experiences the downward pull of gravity. In scenario 2, the upward acceleration of the elevator creates an inertial force that feels identical to gravity. Thus, the observer cannot tell whether they are at rest in a gravitational field or accelerating upward in empty space. This insight, that gravity and acceleration are locally indistinguishable, led Einstein to formulate the equivalence principle. He realized that what we perceive as gravity is actually the curvature of spacetime caused by mass and energy. As Einstein wrote, for an observer in free fall from the roof of a house, there exists, at least in his immediate vicinity, no gravitational field. Einstein's point is that within your local frame of reference, your immediate surroundings during free fall, neglecting air resistance, the effects of gravity seem to vanish. This is not because gravity ceases to exist, but because you and all nearby objects accelerate at the same rate under gravity's influence. Normally, you feel your weight because the ground exerts an upward force against gravity's pull. In free fall, however, no resisting force acts on you, you and your surroundings accelerate together, making gravity locally undetectable. Objects released in this frame appear to float weightlessly, as if gravity were absent. Thus, gravity doesn't disappear. Instead, free fall mimics a zero-gravity environment due to universal acceleration. Einstein's theory of general relativity unified space and time into a four-dimensional continuum, where massive objects like stars and planets warp the very fabric of this continuum. Imagine placing a heavy ball on a stretched rubber sheet. The sheet bends under the weight, creating a depression. Similarly, in spacetime, mass causes curvature, altering the paths of objects moving through it. However, unlike the simplified 2D rubber sheet model, real spacetime curvature occurs in all 4 dimensions, 3 space plus 1 time, making it far more complex. The classic rubber sheet analogy helps visualize spacetime curvature but has significant shortcomings. It only shows 2 spatial dimensions, ignoring the 3rd dimension of space and the crucial role of time curvature. It fails to explain how spacetime behaves inside massive objects, such as within a planet or black hole. It doesn't fully capture how moving objects or rotating masses, like spinning black holes, distort spacetime in more complex ways. Despite these limitations, the 2D model remains useful for introductory explanations because it illustrates the core idea: mass tells spacetime how to curve, and spacetime tells matter how to move. To improve upon the 2D analogy, we can think of spacetime as a 3-dimensional grid, or warped cube, where massive objects create inward distortions. This model provides a slightly more accurate representation because it includes 3 spatial dimensions, allowing us to visualize how curvature extends in all directions. It suggests how gravity works both outside and inside massive objects, unlike the 2D sheet, which only shows external curvature. However, even this 3D model is incomplete because it still cannot properly depict time curvature, a critical aspect of general relativity. In the absence of mass, objects travel in straight lines, geodesics, through flat spacetime. But when spacetime is curved by a massive object, these paths bend, causing planets to orbit stars, not because of a force, but because they follow the curvature. The more massive an object, the deeper the curvature, and the stronger its gravitational influence. Even Earth's gravity is just a result of its dent in spacetime, causing objects to follow curved trajectories near it. Since humans cannot perceive 4 dimensions directly, all visual models are simplifications. The true description comes from mathematics. Einstein's field equations precisely define how energy and mass curve space-time. Planets orbiting the Sun, for instance, are not being pulled by a force but are instead following the geodesics created by the Sun's mass. This is why Earth's orbit appears elliptical. It is tracing the curvature of space-time around the Sun. Einstein's field equations mathematically describe how matter and energy influence space-time curvature. Light does not travel in straight lines when passing near massive objects. Instead, it follows the curvature of space-time, leading to phenomena like gravitational lensing, where distant galaxies appear distorted because their light bends around massive foreground objects. Einstein's geometric interpretation of gravity represented a monumental leap beyond Newton's theory, successfully explaining several astronomical phenomena that had long puzzled scientists. Two of its most significant victories came in explaining Mercury's peculiar orbit and predicting the bending of starlight. Einstein's general theory of relativity introduced the groundbreaking idea that starlight would bend as it passed near massive objects like the Sun, a phenomenon now known as gravitational lensing. The definitive proof came during the May 29, 1919, solar eclipse, when British astronomer Arthur Eddington led expeditions to Brazil and Principe Island to observe stars near the Sun's obscured edge. By comparing the apparent positions of these stars with their known locations, Eddington's team confirmed that their light was indeed bending by approximately 1.61 arcseconds, a result strikingly close to Einstein's prediction. This successful validation made global headlines, cementing Einstein's status as a scientific icon and marking a paradigm shift in physics. In December 2012, a team of Chinese researchers uncovered a striking clue in one of physics' oldest debates, the true nature of gravity. By examining the tiny delay, or phase lag, in Earth's tidal movements during full and new moons, they found strong evidence that gravity doesn't act instantly, as Isaac Newton once believed, but instead travels at a finite speed, equal to the speed of light. Their findings, published in Science Bulletin in February 2013, breathed new life into a centuries-old scientific rivalry. Back in the 17th century, Newton described gravity as a mysterious, invisible force acting instantaneously across space. To him, if the Sun disappeared, Earth would feel the change in its orbit immediately. But centuries later, Albert Einstein challenged that notion with his general theory of relativity. He proposed that gravity isn't a force at all, but the result of massive objects curving space-time, and that changes in this curvature ripple outward at light speed, not instantly. The Chinese study appeared to side with Einstein. If the Sun were to suddenly vanish, hypothetically, of course, Earth wouldn't be yanked into a new path right away. It would continue orbiting the now empty space for about 8 more minutes, the exact time it takes for light, and now evidently gravity, to travel from the Sun to Earth.